such a great job. We have one group left, so at this time, I would like to welcome Jaden, Sam, Alex, Justin, JC, Avery, and Brian to present their project that was mentored by Minh-Duc and Duncan Ryan from Los Alamos National Lab.
Good morning, everybody. For the past 2 weeks, we have been working under the Joint Science and Technology Institute to bring you this presentation over polymer creation and analysis using microscopy.
Let us introduce our team. I'm Alex Urachik, and this is JC Seal, Jaden Chin, Sam Cordero, Justin Lai, Brian Zhang, and Avery Templeton. The first topic that we explored with our mentor, Minh-Duc, is about what polymers are and how they can be used. We explored several different types of polymer, including homopolymers and copolymers. Using string and beads, we built models of these polymers.
Polyurethane foam is a polymer created by the reaction of its own components. We use it every day in modern life in things such as furniture, bedding, etc. It's characterized by a cellular structure that provides a cushion or thermal effect.
Using a two-part polyurethane foam kit, we experimented with several different ratios of part A, isocyanate, to part B, polyol, catalyst, surfactant, and water to see how it would affect the polyurethane foam. We found that higher amounts of isocyanate caused the foam to be harder and more brittle.
After we learned how to make polyurethane foam inside, we decided to take it outside and up the size of our foam. In the box being mixed, we put part B and then part A, which started the reaction and turned the liquid into foam. In the box, it made a foam strong enough to be sat upon as a seat, and even for 3 people to be able to stand upon it. This same method of mixing we used throughout our test, we also used outside to make shapes out of our foam. We all got different outcomes, but used different ways to make our shapes.
Up there on the screen is a nylon 610 polymer made of both a sebocoyl chloride and the hexamethylene diamine. When you combine both of these monomers, you are able to pull out the nylon out of the middle meeting points as shown on the picture on the right.
When extracting the nylon from a boundary layer, after removing one part of the nylon, new nylon will form and the reaction will continue. This process continues until one of the layers runs out and forms a thin string-like structure that can be spooled up.
In order to observe our samples, we constructed our own microscopes out of plastic sheets, a small lens, a flashlight, our phones, and nuts and bolts using a drill. This allowed us to use our phones as an eyepiece to inspect our samples through a well-lit magnification.
We then calibrated our microscopes by analyzing a gray value graph of an image of a ruler. By looking at the pixel distance between 2 of the minimums on the graph, which represent the locations of the millimeter marks, we were able to find the number of millimeters per pixel in our microscope images.
After calibrating, we went to a duck pond and collected samples of worms, eggshells, plants, and a large variety of organisms. Then we took samples of nylon and polyurethane foam, noticing that the polyurethane foam on the right is more crystallized.
We also studied spherolite, which is a spherical semicrystalline region, and it is found in many linear polymers, such as polyethylene oxide. It is formed when many monomers bond together in a crystalline substructure and create many layers as shown above.
First, we measured a small amount of the polyethylene oxide powder on a glass slide and heated the hot plate to 149 degrees Fahrenheit. Then we placed the glass slide in a bowl on the hot plate and waited for it to melt. When it was melted, we took it out and the crystals would form at room temperature.
We observed
the spherulite crystals under our microscopes. We had samples of polyethylene oxide with a molecular weight of 4,600 grams per mole and another with 8,000. Then we examined the growth rate of the crystals.
We observed quick growth and light refraction in the crystals, as well as a cross pattern which represents a refractive index along a radiotangential direction. Additionally, we noticed that the spherulite growth rate depended on nucleation and crystal growth rate.
Based on our results, we found that the molecular weight of the spherulite crystals, the molecular weight of the polyethylene oxide had no relations to the growth of the crystals. And because of our results and the lack of resources we had, we weren't sure about the consistency of our data.
Among other applications, polyurethane foam can be used. Among other applications, polyurethane foam can be used for insulation and cushioning. Nylon can be used for rope and bristles on a toothbrush. And polyethylene oxide can be used for lithium-ion batteries and biomedical applications.
While it is true that plastics cause a lot of harm to the environment, they actually cause a lot less harm than most paper products do. The amount of energy it takes to make a paper product is actually a lot more than used to make plastic products. And aside from that, you'll probably be using your plastic boxes over your cardboard boxes.
We'd like to say a special thank you to our mentors, Dr. Mai-Hee Kim and Dr. Duncan Ryan, as well as Los Alamos National Laboratories, the Defense Threat Reduction Agency, Oak Ridge Institute for Science and Education, and UNM. Thank you.
I would like to say a great thank you to all of our students who not only created a research poster on their project, but also spent time putting together these quick 5-minute Ignite presentations without the use of many words on the screen and relying just on visuals. So on behalf of all of us at ORISE, DITRA, LANL, and Sandia, we are proud of the hard work each and every one of you put forth during this 2 weeks. Give yourselves a round of applause. At this time, I would like to play a short video for everyone to view that shows a summary of what our students engaged in during these past 2 weeks.
I'm biting my lip not to say your name. Tighten my grip, but it stays the same and it's over.
Okay, let's try this again.
JSTI is the Joint Science and Technology Institute that is sponsored by DITRA, the Defense Threat Reduction Agency. Each year, we have the opportunity to bring 36 students to Albuquerque to engage in hands-on research with national lab scientists from Sandia and Los Alamos so that they can take part in this real-world scientific research process and actually hope lead them into pursuing a STEM career once they get out of high school and into college and beyond to increase the number of students that we have entering the STEM pipeline.
It's a once-in-a-lifetime opportunity where you're going to
Yep. Gotta love technical difficulties.
Scientists from Sandia and Los Alamos so that they can take part in this real-world scientific research process and actually hope lead them into pursuing a STEM career once they get out of high school and into college and beyond to increase the number of students that we have entering the STEM pipeline.
It's a once-in-a-lifetime opportunity where you're going to a faraway place for 2 weeks and learning about different things that you wouldn't be able to learn in high school or college.
I know for me, I never really got a good example of applicable science that we were learning in school, especially with STEM things. I never really had a really good idea of what those would look like in a professional field. And I've learned a lot, not only about things that I might be interested in the future, but just more, I guess, applicable ways of applying the things that we're learning in real life.
They take you on different field trips to go to do some fun activities, and especially STEM activities as well.
It's a great opportunity to meet people from all over the country, and especially when you're in your own state, you're often confined to your own perspectives, I guess, and so being able to meet so many new people and mentors from all over the country really gives me the opportunity to sort of explore different perspectives and understandings that I hadn't really thought of in the first place. And so I really like this program because of that.
I've been someone who's really interested in computer science, especially artificial intelligence. So finding a way to really actually use what I've learned and use the things I've learned in the past in the real world, not something that's purely theoretical, is an experience that truly is unforgettable, and I don't think any other program that I've seen so far is able to supply this, so I definitely go to JSTI.
Not only do you get to do a lot of fun STEM things that you wouldn't normally do in a classroom setting, but you also get to do a lot of fun social activities that, you get to make a lot of friends that you wouldn't, normally meet, since they're all from different places around the country.
So good! So good! So good!
On the scientific side, I think they try to mix people up into fields they're not so used to. I think it's a really cool way of finding, this interests me, or maybe this doesn't interest me. I think it's a fun time. We don't just do research too. We get to go to amusement parks, zoos, the whole bit. I feel like I've seen everything there is to see in New Mexico. So yeah, I definitely recommend it. It's a good time.
I don't know, just I want to get the word out there, and I want to thank everybody who's involved with JSTI. This experience that I've had could have not been possible without the help and support of all these people. So.